So today we will again read about particle physics, and this is our third lesson in particle physics. So today we will read about conservation laws. Then so here what we will read is on reactions, like if we have a reaction, how we check that if the reaction is conserved or not. So we will say if the reaction is conserved, then it will be said as allowed, and if not conserved, then it will be said as forbidden. And secondly, if we see that if it is allowed, then we will try to know that it follows which interaction. So first we have to check whether a reaction is allowed or forbidden, and if it is allowed, then it follows which interaction. So to check this, we apply conservation laws. Now conservation laws can be said as universal conservation laws and approximate conservation laws. So you must be wondering what is universal and what is approximate. So under universal conservation, that is exact conservation laws, we will check energy momentum, second we will check angular momentum conservation, then we will check charge, then we will check lepton number, baryon number, and CPT theorem. Done. And in approximate conservation laws, we will check isospin. What this means, we will discuss it. Third component of isospin, of I, that is I3, or we will denote it by IZ. Then third, strangeness. Then we have hypercharge, then parity, charge conjugation, time reversal, CP violation. This we denote as E and P. Angular momentum by J, charge by Q, lepton number by L, baryon number by P. This is I, this is I3 or IZ, this is S, this is Y, this is P, this is C, this is T. So these are our universal or exact conservation laws, and these are our approximate conservation laws. In universal conservation law, we will check energy. So for a reaction, if left hand side mass of particles is greater than right hand side mass of particles, then the reaction is allowed. And if left hand side mass of particles, but if left hand side mass of particles is less than right hand side mass of particles, mass and mass of particles, okay, done, then in generally it is not allowed. But here also we have special case. In special case, this is allowed. When is it allowed? In the presence of strong nuclear field. because here the kinetic energy of the particle is highly increased which balances the mass of the particles. So the reaction is allowed, but it is in a special case. Now we will see what we mean by isospin. So what is it? It is a quantum number related to the strong interaction. Second point, we can say it is a dimensionless quantity. And is not actually any type of spin. Third, we can say it is vector quantity, in which up and down quarks have value of isospin as half. Okay, it has three components: Ix, Iy, Iz, which are coordinates in the same 3D vector space. And the third component is the third component of isospin, that is Iz. So nucleon, for example, we will say nucleon has a property which we discussed earlier called isospin, which is mathematically analogous to spin. Now proton and neutron are considered as nucleon with different values of I3, but they are considered as nucleon, and the nucleon has isospin value of half. So both have isospin half. The third component of isospin will be minus half and plus half, that is minus I to plus I, that is I3. Light mass particles cannot decay into heavy mass particles, but the vice versa is possible. Which means heavy mass particles can decay into light mass particles. We said lepton number conservation. We will have to check for a reaction. Let us say neutron decays into proton plus electron. For neutron we have energy 939.6 MeV, for proton 938.3 MeV, and for electron 0.511 MeV. So we checked, and for this energy conservation is possible because mass of left hand side is greater than mass of right hand side. So we will check lepton number conservation. Decays to proton plus electron. So neutron is a baryon, okay, proton is also a baryon, but electron is a lepton. So lepton conservation does not hold, but if we check for baryon conservation, yes, baryon conservation do hold. And for lepton conservation we will have to keep one thing in mind, that is lepton is plus 1 for all leptons, minus 1 for all anti-leptons and 0 for all other particles. Now if we have a reaction where electron and muon is involved, so we have to separately check lepton conservation for electron and separately for muon. That is, lepton number conservation must be separately conserved according to generation. That is, that must be of the same generation. So we will check for Le to Le conservation, L mu to L mu conservation, and L tau to L tau conservation. Electron to muon or tau, muon to tau or electron or any other thing is not possible. That is, Le to L mu or L tau not possible, but these all are possible. For baryon number conservation, baryon +1 for baryons, -1 for antibaryons, and 0 for other particles. So we will have to check baryon number for left hand side and right side of the equation. Now third component of isospin, that is Iz, or we can say as I3. It has multiplicity of 2I plus 1. That is isospin, where I here is isospin. Let us say for doublet, what we have in doublets? We have nucleons. So in doublet we will have 2I plus 1, that is m is equal to 2. So 2 is equal to 2I plus 1, which implies 2I is equal to 1, I is equal to half. So for nucleon we have half I, and I3 we know it runs from -I to +I, including 0. So we will have -R and half. For triplets, m is equal to 3, so 3 is equal to 2I plus 1. Solving we will get I is equal to 1. This one for pions, we will have -1, 0, 1. Multiplicity 3, the multiplicity 2. What I was saying earlier, as in any strong interaction, there is no distinction between proton and neutron, and it treats both as same entity. But in EM interaction, both can be distinguished as different charged states of the same entity called nucleons. So the idea of spin originated from the fact that nuclear forces, that is strong interaction, are charge independent. These are charge independent. We will calculate isospin for various particles. So first we will get to know that particles in nature occur in multiplet form. So mesons, we have pions, which are pi plus, pi 0, pi minus. So these are triplet. Then we have kaons, which we have k plus and k0. This is doublet. Then we have eta, that is eta, it is singlet. Then we have baryons. Here we have nucleons, doublet, sigmas, sigma 0, sigma plus, sigma minus, triplet, cascades, minus 0. This we have as doublet, and lambda as lambda 0. This is singlet, and omega also singlet. Now note that I, that is isospin, is same for all members of multiplets, that is 2i plus 1 is known as multiplicity. Now we will calculate isospin as we said for nucleons. So all doublets we will write together only. We have nucleons, cascades, kaons. These three we have in doublet form. So here 2i, let me write it doublet. 2i plus 1 is equal to 2. So from here I we will get as half. So I is half for nucleons, that is neutron, proton, cascades, that is minus 0, and kaons, k plus and k0. For all this I is half. Now we will write triplets, all the triplets which we have known. Let's say pions, sigmas, these are known. So for this 2i plus 1 will be equal to multiplicity 3. From here I we will get as 1. So I is equal to 1 for pi minus, pi 0, pi plus, and for sigmas 2, that is sigma minus, sigma 0, sigma plus. So triplets I will be 1. And now let me write lastly the singlets. We have eta, we have lambda, and we have omega. For this we will have 2i plus 1 is equal to 1, which implies I is equal to 0. So for eta, lambda, and omega, we have I is equal to 0. So we have calculated the isospins for baryons and mesons. Here only we will show the isospin, means third component of isospins values. The value from minus I to plus I including 0, dot 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 dot. It has whole lot of isospin values. So for nucleons, we have I is equal to half, that is for nucleons. It will have value of minus half and plus half. Minus half for neutron and proton plus half. Similarly for cascades, this will have minus half and half. For kaons, it will have minus half and half. But here minus half we denote it for K0, plus half for K plus. For pions, sigmas, isospin value is I. So here we will have third component of isospin as minus 1, 0, 1 respectively for pi minus, pi 0 and pi plus. And for sigmas, similarly we will have minus 1, 0 and 1 respectively for sigma minus, sigma 0 and sigma plus. And for eta, lambda and omega, as we have I is equal to 0, so the third component values for all of this will be 0, that is I3 is equal to 0. Now we will discuss strangeness. Concept of strangeness was introduced in order to make the distinction between strange and non-strange particles. So strange particles, let me write it as strange particles, it has two specific properties. So first, associated production and production via strong interaction and decay via weak. So kaons and hyperons are produced in pairs, never singly. This is called associated production, and these particles, that is kaons and hyperons, are called strange particles. And strange particles have another property, that is production via strong interaction and decay via weak interaction. But here we have an exception of sigma 0 because it decay via EM interaction. So we came to know the strange particles are kaons and hyperons. Now for an example, we will have pi minus plus proton via strong interaction will give lambda 0 plus K0. That is, these two particles are strange particles. It is produced via strong interaction. Now it will decay via weak interaction and it will give proton plus pi minus, and for lambda and for kaon we will have pi plus as pi minus. Now here we will see an interesting fact that both of these are non-strange particles. So we will get to know that non-strange particles in presence of strong interaction produces strange particles, and S, that is strangeness quantum number, it will be 0 for non-strange. We can write isospin, means third component of isospin, in terms of charge, Gellman Nishijima formula, as Q is equal to I3 plus baryon number by 2. So now we'll check the assignment of strangeness for elementary particles. For First we will study for kaons. For k plus q is equal to 1, I3 is equal to half, and baryon number is 0. So we get to know that strangeness is 1. For k is 0, we have q is equal to 0, I3 is equal to minus half, and p is equal to 0. So strangeness we will have as 1. For hypers, that is for sigmas, firstly for sigma plus we have q is equal to 1, third component of isospin is 1, and baryon number of 1. So strangeness we will get minus 1. For sigma 0, we have q is equal to 0, I3 is equal to 0, baryon number is equal to 1. So strangeness will be minus 1. For sigma minus, we have q is equal to minus 1, I3 is equal to minus 1, baryon number 1. So strangeness we will have minus 1. For cascades, similarly you can check for cascade minus and cascade 0. For both we have strangeness of minus 2. And for lambda, we have strangeness of minus 1, and for omega we have strangeness of minus 3. So if we like to summarize that, we have strangeness of 1 for kaons, all kaons, strangeness of 0 for non-strange particles, strangeness of minus 1 for sigmas and lambdas, strangeness of minus 2 for cascades, and strangeness of minus 3 for omega. And we can note an important point, that is strangeness is for antiparticles is negative of the corresponding particles. Another important point, we have delta S should be 0 for EM and strong interaction, it will be 1 for weak interaction, and in general 2 is not allowed.